Welcome back. I was thinking I would continue through the periodic table. Probably a good place to start is this cool little thing I made today. Let's see if I can get this a little bigger even. Nope. Nope. Maybe. If I fit the screen, it'll make it real small. Okay. So, neutron, real basic. I try to make it as basic as possible. Maybe it needs like a little explanation, but unfortunately, that's so be it. Maybe this row maybe could be dropped a little bit too. Besides the point, in short, hydrogen 1 1. So to go back to just hydrogen. These ones. So it's basically this a polygon with a channel, a current. So it doesn't. This is the problem with what I did is it doesn't really show that this is what's happening. Maybe I should draw an example somewhere. Like a polygon chamber. Just on like one of them as a representation. Okay. Anyway, so current comes in, creates an eddy inside of a polygon, which behaves as a proton, and then it can build a mass, which then pushes the boundaries of the polygon and makes it basically behave as a neutron, and then also still has an eddy, so it behaves as a proton and a neutron with a current, which is the electron, in essence. And then, again, two neutrons. And this time, this is when the current just breaks through this boundary over here and just goes right through. And so it just becomes a straight line with either one nucleus or neutron or two neutrons. So it kind of looks a little weird here, but once I start branching out here, it makes a little more sense. Okay, so lithium 3.6. I was also thinking like this is based off of an island, which is obviously a little questionable to some people, but regardless of what it's based off of, it could be done up, down, but essentially it's a reasonable way to approach it. And from its beginning, even if like the first few steps, if it at some point, like if it arrives at here, then we're pretty much on course. So it doesn't really matter all that much, but this is probably how the neutrons just generally arrange is they do one top. So this is what I was thinking. They do one top and then top bottom. And then they do bottom again. So they start on one side, go to the other side, do the other side again. But then they're all the way over here, so that again the other side. And then it comes in here and does this side. Or here maybe, I mean, it may do, like rotate around this way, go here and then here. to essentially arrive at this, where this is here in truth. I don't know. I'm kind of assuming that it splits the last ones and spreads out, and then it fills in behind it again here, and then at that point we got the beginning of a backbone. Whether or not this makes sense in is the actual like conclusion of this approach is unclear at this point, but it does appear to match the isotopes. That's really what I'm going by to determine if the method of analysis is plausible. Is it arriving at the isotopes like soundly, like here, where it's like a stable system that repeats, a stable system that repeats, a stable system that repeats, a stable system that repeats. Like this one does not repeat. This one over here, I noticed that these two repeat, so maybe I should put that in with the color. But notably, like even though they're not symmetrical, they're so early on in the periodic table that they're still able to be stable because there's probably just not that much current involved. Like the higher up here, it just takes more current within the polygon, shaping the interior of the polygon to really begin to add complexities. So I'm thinking down up here at the carbon nitrogen range, like it's possible to have this asymmetrical aspect to the neutron arrangement without it being unstable. So it just can and it does. And but like that's not normal. That's only like an exception to the rule where like once it begins to grow, it really needs a symmetry to it. Not asymmetry, but and it needs symmetry. And it tends towards, it's not absolute, but it tends towards symmetry to the point where sometimes it skips one of these. It's like, nah, I need both of these. Okay, let's keep going. So this stable one repeats, and then we just add another. So, and what's happening here is essentially like, why does it matter that it's stable? Like what is happening? These proton numbers, 1, 2, 3, are the number of eddies forming and channels outward that are like the tails to the eddies that then just produce essentially the proton number. Where exactly they position themselves, I'm not sure. But these are just like current eddies that are caused by like surrounding structures that are like mountains in comparison. So like a lake is gonna be shaped by the presence, or a river is gonna be shaped by the presence of a mountain. Like in the same way, the current, the eddies, their positioning depends on the actual shape of the interior polygon and the positioning of the neutrons, leading to a certain number of stable eddies that can form, producing essentially like spaces within the chamber where energy and current can flow. Okay. So over here, like it's not stable. If we wanted to say 4, like add another proton, then we're adding another eddy. And what's another eddy gonna do? It's gonna cause pressure to like separate the materials. It's just not stable. So it's more stable to just add another mass, another neutron, and then even then it still really needs another neutron still before it can add a proton. So there's this like balancing act going on between the masses producing enough eddies or positions for eddies, but then it goes up to, again, up another neutron to this stable one. This one's stable because it has just symmetry. So it's just more stable. It's not like the currents are flowing like this way and causing like separation of the particle because it's easier to flow through the less resistance. Over here it just goes right down the middle. So it's very stable of a setting, and so as currents increase, then that would produce basically the capacity for this same stable arrangement to have more eddies. It doesn't have to have 5 with this arrangement of neutrons if it's a stable arrangement. So because it's stable enough, with an increased current, another eddy can form, and then it just is carbon with the same neutron arrangement. But then carbon, like, adds 1 and then adds 2, and this one's a little anomalous. I'll admit this is anomalous to what I'm saying, to this analysis that carbon 14 is radioactive to the point where it just decays into nitrogen 14. But my thoughts are just like I was saying, so like maybe I can't like explain it with mathematical equations, writing out the precise, like, technical exactness of how, like, well, when there's 8 mounds and, like, it just caught, like, six eddies basically means the current is low. It's just not really sustainable. And so one of those, or not, the current is low. The channels are small, so the velocity through the channels is high. So it basically blows one of the neutrons out, but the space that it had shaped the polygon remains, and so an eddy is able to just take the place of a neutron. So it just goes from this like less stable circumstance just simply because of an imbalance of like the number of eddies to the number of mounds where this current is passing through. So basically it can decay here and lead to the same structure. So this one does interesting. This is a bit anomalous, but I think that does explain it. That's my thoughts. Obviously, people can have their own interpretations. Okay. So this one again, this structure just repeats with nitrogen and carbon and oxygen, and which makes sense because of its not only symmetry, but it's like it's mirrored symmetry. Like it's really symmetrical versus like this one's not quite as symmetrical because it has the sharp points on it. This one's much more like hexagonal, pretty much more rounded. And so it's able to basically stay stable while the current increases, which then takes it from a certain number of protons, of eddies, of spaces within the body where currents flow in eddy shapes, which are like blown up regions that allow for just like the storage of energy of current within it. And so they, because of the stable arrangement, are able to go up to 8 eddies, protons. And then oxygen is the only one with this unstable asymmetrical arrangement. And then back to symmetry, we can repeat again through fluorine, where the only fluorine isotope that's stable is in this like tri set here. And then into neon, which then has again the only one with a asymmetry, and then again neon with a third isotope. That is again more of a stable mirrored asymmetry, which then repeats again twice, where sodium is the only one. And then sodium's only isotope is in this pattern, that is. And then magnesium. So in essence, this pattern again, just to think it through, that current is coming from an inlet, passing through a body that began in a shape like just a single chamber, that then had a outlet carved and began to just make mounds, to a point where it arrived at mounds in this shape of the neon, the 12 neutrons here. And then the current continues to increase, which then just allows for more eddies within the mounds without causing like a fracturing in the mounds, until 2 more eddies are able to form. And then in order for more eddies to form, the next proton requires a stable system, so it doesn't use the asymmetrical structure. It comes in once there's a symmetrical structure, and then its only isotope that's stable is again in that symmetrical structure, which then again jumps over to the next element. So again, that stable structure just is able to stay cohesively together so that more eddies can form within it because of its symmetry. And then again, it just adds to the end another particle which doesn't have other elements with that same 15 because it's not symmetrical. And then again it adds to the end, and again we go through the same sequence where there is a stable arrangement that repeats of 16 that arranges like this based on current flows, 16 that arranges like this based on current flows, and then again. And so this again, it just is a stable like nucleus that allows for current flows into it to allow for eddies to form, which are protons, which are basically like empty regions in this body, this conglomeration of material that's like a rock that just has eddies forming in it, that each one of them allows for a flow of a current. And so those each are like protons, where the rock itself is the actual mass of the proton within the region of the eddy, but in the regions where there is no eddy, it's just like solid rock. Like that's a neutron kind of thing. But in a way where it's like it is energetically causing this to occur. Like we can't necessarily just see it in as any rock, although we can see it in places, but that's besides the point right now. So this structure repeats 3 times, and then again an asymmetry. So through a single stable isotope for phosphorus into sulfur, which then has the only asymmetrical this, and then it comes to another symmetrical structure. And then interestingly, sulfur again is able, with the same number of eddies, it's able to extend further and just form additional neutrons at that point. And then this structure of sulfur 34 is repeated in chlorine 35 and in argon 36, whereas this structure of sulfur 36 is repeated not just in chlorine 37 and argon 38, but also in potassium 39. And then also in calcium 40. So 5 times 20 neutrons arrives on the show. And that makes sense because the first stable one's real early. Like, it's like, what are you doing in sulfur? Like, based on this one over here, like, it required 14 to have this. It's able to add 4 neutrons in here, another whole layer of neutrons here, just added to it with only 2 additional protons. That's pretty unusual, and it makes sense, therefore, that it would be able to like extend in the other directions, almost like it's just barely reaching in. And then in the other direction of higher protons, like it's barely stable with 20 neutrons with only 16 eddies. Like, it really needs more eddies, but it's able to be enough to be actually stable. But because it's just like on the cusp, it allows for the other end to reach further into the point where it's into calcium. This is all I did on this one. Let's just finish through here. So again, potassium runs into 3 at the end, which does repeat with calcium. I didn't draw that. I didn't realize, I don't think. I started looking like, did some of these ones that I just didn't think actually repeat? Like, that's not actually repeating because it has an extra line. But this one, 1, 2, 3, 4 plus this, 6, yeah, it's 21, 21. It's definitely repeats. Also, I was thinking like top, bottom, bottom, top, top. So here maybe you should go bottom instead, and then top, and maybe top, and then bottom. I don't know, that would be interesting. And then, but this should go up, down, down, up. Skip this one maybe because it's kind of one or the other almost. Like they're almost like the same thing. Like this one's just nitrogen and waiting. Like any moment it's gonna be nitrogen. So it's pretty much just consider it kind of nitrogen. So it was down there, and then it moves up there, and then it fills both of them. The idea generally being maybe it vibrates, and it would probably be good to depict it. Okay. So this structure repeats potassium 41, the neutron structure in calcium. And then let's go back to here, I guess. That's where I was on here. Way less cool looking. I made it all the way, though, to zinc. So I was thinking, like, maybe this isn't reasonable how I'm doing this, rows of 4, but like it because it's matching the isotopes, I've just been following this path. Like at some point up here, right here, or at this structure, or no, at this structure, there's an option kind of just to start extending outward instead. And I initially did that, but then I realized that the isotopes really match this approach. Whether or not this is actually accurate or is just like mathematically fitting enough to like follow the pattern out and just like representing some like edge of growth that I'm like missing the overall growth, but like capturing the essence of the edge of growth enough to see that it's happening like that, and missing like how it structures itself. I'm not sure if that's possible though, when it seems to keep resonating around this 4, like that it's rows of 4 is like, it seems like if I just put one there, it would just go out of whack. 1, 2. So if I put 2 there, that would pretty much be, instead of this one, it would have 1 up there, 1 down there, and there, and there. Which maybe is possible for chlorine. Maybe that's why chlorine's all like chlorine-y. Like it resonates between certain arrangements of these. I mean, I'm certainly just scratching the surface of what this really could be about. Okay. So where were we? Calcium. Calcium. So then, whatever this one is. I don't want to say scrotium in case it's not scrotium, and I'm pretty much just saying scrotum. Now I'm just doing it though. So scrotium or strodium, strontium. Oh no, that's not it. Let's see. Scandium, scrotium. I kind of thought it was right. It's like, no, I think it might be, so I'll just say it. Worst case scenario, it's wrong and kind of funny. But now I know it's wrong, and I just said scrotium. Oh my god. Okay, so this one. Certainly I'm just like ignoring like the electrical charge aspect of this and just totally focusing on neutron arrangement, which I think has a certain element of it, of like more like composed of all the parts maybe to it. I don't know. So maybe I can just continue to extend this. It might be a little absurd. Canvas size. 9,000. It's over 10,000. Might as well, right? Let the IRS know. Bank's like, excuse me, sir. I once took out $9,990. And I just was like, yeah. Okay, what have I done? How do I, like, move ever? Select all? Move it? Oh. Oh no. Okay. Well, that's lame. I guess I'll just for now hit new. Go big or go home. That's what they say. Am I right or am I right? Lord. Let's add a little gradient overlay. Nothing too, maybe some cloudy. Something a little cloudy. Oh, that's nice. That's pleasant. That's pleasant. Okay, okay. We don't want to rebuild the wheel here. So I've heard. Reinvent the wheel, pardon me. Rebuild the wheel. Oh, we are doomed. I know. My apologies on that front. Okay, maybe something. That's not. Why is that not doing anything? Like, shouldn't that do things that I just did? Seems not to be. Maybe it's really resistance to change because of the color. Whatever. You stay the same. Okay, so grab my notebook. Okay, here on out in this video is gonna get real slow, so just a heads up. If you wanna stop watching, or maybe just start skipping ahead and watching this progress more rapidly, by all means. But also, I'm gonna be talking, so by all means, stay and we'll hang out. So yeah. Okay. So we need to begin with. Let's start with a nucleus here, kind of thing. This here. Hopefully I can copy that. Where did everything else go? Wait, where did everything else go? Oh well, alright. We're drawing anew. We're starting anew. fresh starts. I was on 20. I guess I didn't write it down. So this is a mess. So maybe I'll just start with the periodic table like a... Okay. We doing it again? We doing it again? So last element was calcium. We're on to scandium slash scrodium, whatever you want to call it. If Scandinavia wants to give this up for certain, half the population, like to honor. I assume it's got some relationship to Scandinavia. I don't know. Let's see. Isotopes of scandium. Okay, we got one isotope, 45. That's it. 45, just like that. Boom. 21st. 21 eddies up in this polygon. Okay. And then... what size was I doing here? This was 72. These were 48. So let's keep it thereabouts. Okay. Okay. Although I would probably be like, this is 24. Let's look ahead a couple elements. I'm just trying to like make sure I capture the elements of the previous one if I rewrite them that are repeated. Like if the same neutron structure repeats, maybe this one where there's exactly 20 neutrons, and so it doesn't look like it. We got 24, so maybe that's this one. So maybe it would be good to repeat this one. Let's go on to the next one though. Titanium. Titanium's got a lot. We can at least look at this here. 46, 47, 48, 49, 50. 46 through 50. That's a lot. But it also has... Oops. Let's copy that one. Copy, paste. Paste. Okay. Okay. Cool. This one can just be calcium. Okay, and then paste again, maybe? Okay, cool. Then we're gonna just jump to titanium over here. Sometimes it seems like just clicking the thing would make sense, but it's too technical for me sometimes. Okay. Okay. 25, 20, I got 40, 40's, okay, through 50. So maybe we got enough room here, realistically. Copy those three, paste. To put the next 4 here. Since it's 5 titanium, it would probably be nice to group them. Then I can maybe put this one with a little space. Dot, dot, dot. Okay. Because I really don't need much space as this grows because of the way I began to structure it on the last page. Okay, are these just together? No. I don't know if I really spaced them well. Let's make those equidistant. Okay. Whatever. It seems fine. Okay, so now let's just cut a line across here. Real simple like approach, that's what I'm gonna do. Put a line across, okay, okay. And this one is, alright, let's take these three. Oh, why is it moving the back? I guess I grabbed the background. Where? Oh, no. Let's just move these significantly over. Okay, that'll give me room just to like continue on from the last page pretty much. Okay, and this one, this real quick, 47, 48, 49, 50. Okay. So the really stable one, pretty much. This is the most stable when it has the 2 on both ends, I think. It seems like this one had 5 of the same structure. That's a lot. 5 different amounts of eddies that stably form. Okay. Let's just copy this one over here. Oh, God. Why is it merging layers to copy a line? Okay, no copying lines. Actually, I kind of would like to... Let's get a rectangle, though. Involved. Okay, rectangle is a go. Okay. Neutron is a go. No. Just copy and paste. Why is that not a thing? Lord, help me. Pardon me. I know I'm just doing some weird character thing a lot. That's probably annoying. No, it doesn't. Off. And they're attached. It doesn't make sense. Oh, God. Duplicate. I really want these to look nice, or I'll just be like, tap with the pen. I just don't think I can do it. It might honestly be more more possible than... Okay. Let's make that white. Okay, get that at the top. Bigger fonts. Probably the font I used over here. What was that one? Euphorogenic. I guess not on this list unless I find it. Also, what size is this? 72? 72. I was hoping I could kind of let's just make this. Why is that line visible underneath it? That's what I'm confused by. It's full, it's not opaque, or it's opaque. Full opacity. Okay, whatever. Okay, so this structure, though, now that we've created the structure, we can just grab all of its components, copy, paste, undo, get that number in there if I can. And so because that's also 24, it's also 24. It's also this arrangement, I guess. Presumably, obviously, I'm just kind of going through it to see if that's the case, but it seems really fitting. So, like now, titanium goes through not just 1, 2, 3, but 4. What have I been doing? I've been just adding systematically rows of 4 to a point where I started to number them. Like, this is getting, like, really tedious, just adding all these dots, like, outward. I'm just gonna put this block with a number, and then just start drawing its boundary around it of the dots, which is really always beginning with this, and then always with a center column of 4, it seems, and then just a 1, 2, 0, 0, 1, 2, 3, or 0 back to 4. Adding another in that column, so I mean, like the fact that there are 4 and it reaches to just 6, the same exact structure to the point where I can just go like this. And it's correct for this structure here. All I need to do is change this number to a 6. Get that out of there. Where is this one? There we go. Done. Just like that. And then I can copy it again. Bring it here. Do the same thing. Get that out. 6. And then just get rid of one of these. Boom. And then get this here. did it? I don't know. I'm a little confused when it does that, but... So we don't need that. Just leave it as an outlet, pretty much. Inlet, outlet. I don't know if it really makes sense, though. I was trimming them off because it kind of has, like, up there, too. It kind of like a cross. So that's just... cut that back. Okay. And then... this one... just needs one more proton. So pretty much just draw a line here. Copy, paste. This. Okay, maybe this is a little in need of some adjustment, like down there. Okay, something, whatever. It's fine. It's just kind of janky looking. Maybe I'll just grab all three of these, move them down. Okay, that's a little better. Okay. I'll make this one nice so I can use it as a base. Pretty much. Whenever I want to do 3. I'll use this one especially. Although, with that in mind, maybe it would be good to have these all a little closer in. Just to indicate there's space for like another thing. Probably be good if I'd just done them collectively. Pardon the boring parts. Okay, so we're through titanium. Like, it ends on a stable one. That makes sense. So that's cool. Okay, then after titanium is vanadium, which has... two isotopes, one of which decays into this, but it was enough that I wrote it. Let me see, isotopes of vanadium. Weakly radioactive vanadium-50. So this one's can decay, but it's really not that unstable. Okay, so after this we go back to this. Alright, vanadium. Or wait, let me see. How many? It's 50. It's 23, 50, and 51. So this one. Yay, I got them all. Okay. .3, so we just go up there. Just another eddy within this structure, able to stably form that decays to a degree. Like its half-life is 1 to 10 to the 17 years, so really like it's pretty stable, but it's not as stable as the one that has this structure here. So copy that structure. I'll probably color code this after. So that's the two stable isotopes of vanadium, which again makes sense in that it's stable on this one, and this one is the same. And these three again are stable across them. This doesn't have another one, at least not yet. Let's see what the next element has. It's possible some of these, as we go forward, like we're gonna see more we're gonna see more crisscrossing where the titanium goes down to 46 and up to 51, and then this starts at 50 and 51, but like the next one could go down to like 49. I don't know if that happens yet, but I'm pretty sure it happens. So that's chromium isotopes. In terms of just stable isotopes. Okay. Chromium 50, 52, 53, 54. All stable. Chromium is 24. So we want a 26er, which is this guy, which makes sense to be stable. I don't know if that number is chosen. Okay. Here we go, here we go. I believe in you, baby. Paste. Okay. It would be probably beneficial for me to like work out ahead of time like which ones have this structure and just keep doing this. I might also, this is 6, okay, 24, 27, 28. Okay, we're good on those things. Chromium also, is this one stable? So let's just go ahead and do chromium 24, 50. Got the number. Oh, I got so many freaking so many little things on this. I think it bogs it down doing it like this. There's got to be another way. Maybe I have to group them. I probably could just group them without the number and then just add the number after. That seems fine. Okay. 52. 24. CR. Boom. Okay. Then it's also 53 and 54 though. So we can pretty much go with this one since I made it nice and pretty. Copy, paste. Okay. This one, also this one. I'm just going to move this up a little bit. Actually, I guess I need to move them all up a little bit. Let's move them all up a little bit. Not that. That should do. Okay. Whatever. Maybe that one a little bit too. Pardon me. I could do this off camera, I guess. Do the more, like, just the more, like, get to it kind of stuff on camera if I'm gonna be doing this. Okay. So I guess, it looks like I'm gonna be just doing this for a while, so maybe I just will stop. Sorry for stringing anyone along to watch me doing this for a while. It just seems like what am I really gonna do unless I finish this and then I talk about it just in the same way as this one. Like now we're starting to get somewhere though. We were here. Now we're getting through pretty far into. That's good. I'm just curious if we're gonna start noticing different patterns as we get into further into the isotopes because I don't know. I don't know what we'll find. Obviously, if this is true, I'm pretty sure it is. I'm pretty sure this is straight up legit, and maybe it's not exactly accurate, but it's straight up legit that this is happening. Just a matter of figuring out. That's why I'm sitting here. Like, I don't usually put this much attention onto a file. Like I think this is legit. Made it nice and legit looking. Just legit. Too legit to quit. I guess that's probably a good title for this one. Alright then. I guess until I'm back with some more of this. See you guys soon.